So today things get really fun because if you'll notice the title of the note says difference in proportions, meaning now we're going to have two different population proportions that we're comparing to see maybe if the proportion of one is larger than the other or if they are different than each other. And so the null hypothesis, the good news is the null hypothesis is going to be the same every single time. It says, what's the usual null hypothesis for a test about a difference in proportions? And we're always going to assume the null hypothesis is true. We're going to work under the assumption that, think about what this says. This says if I take population proportion 1 and subtract population proportion 2, I get nothing. What that means is they are the same. So in other words, or symbols, and other symbols, if you will. We're going to assume, we're going to work under the assumption that the population proportions are the same. We're going to be trying to find evidence for or against the alternative, which is going to be maybe one of the population proportions is larger than the other one, less than the other one, or maybe they're just different. Be sure right here, I noticed on your test last time on the free response question that had two different populations in it. Some of you are struggling on those with defining both parameters. So I'm just going to make a little note here, always define parameters. So tell me exactly, explicitly, what are you assigning to P1? What is your population 1 in your formula? It's imperative that you do this because technically you have the choice of assigning either or. So you have to make sure that the AP grader sees right away what your first population and second population are. So be sure you do that. All right, the inference method that we're going to use is called a two-sample z-test. Last time we worked on one sample z-test for a population proportion. This is a two-sample z-test because we're going to have two populations, a sample from each one. Z-test meaning that we have to standardize the statistic. We're performing a significance test. So it's not a z-interval, it's a z-test. And specifically not for one population, but a difference in proportions, population proportions. What is the pooled or combined sample proportion and is it on the formula sheet? So here are the conditions for conducting this two-sample z-test. These should look very familiar. Just glance at these. Random, the data come from two independent random samples from two groups in a randomized experiment, or from two groups, excuse me, in a randomized experiment. 10%, just check both populations. Both sample sizes are less than 10% of the corresponding population sizes. You don't have to do that for experiments. And then the large counts condition is going to be a little bit of a beast here. We've got some new formulas showing up, of course, just when you get comfortable with these. It says that the expected numbers of successes and failures have to both be greater than or equal to 10. Well, yeah, we know that. But this time what we're going to do is we're going to do what's called pool the samples, combine them, combine the samples. So you're going to see this on the formula sheet, this p hat with a little subscript c on it. Let me see if I can grab my formula sheet really quickly. Hang on just a second. Okay, here is on the back of your formula sheet when you're dealing with two populations and you're assuming that population proportions are equal to each other. Here is the formula that is right there in the notes that I'm about to talk about. And essentially, you're just going to put the total number of successes, you're going to add the number of successes from each population, that's what that capital X is, and put it over the total sample size. So add the sample sizes together. That's going to give you p hat sub c, which you notice we're going to need in the formula for the standard error of this statistic, okay? So don't be too scared yet. This p hat C, you can think of it as just the combined statistic. This is on the formula sheet, so I'm going to go ahead and highlight that. Number of successes total over the total sample size. All right, then you're going to use that to plug into the large counts formula. So this is the fourth variation of large counts that we've seen. Sample size of population 1 times the pooled sample proportion, and sample size of population 1 times the complement of that. Those have to be greater than or equal to 10, and then the same thing must be true about the second population. All right, when you get to the part where you're trying to find the Z value, the standardized test statistic, well, there's our friend, the general formula, and this is kind of a beast here. But this is on your formula sheet, okay, on the back. The statistic part, you'll just have to know we're taking the sample proportion from each population and subtracting it. Here is why it's really important for you to define what your population 1 and population 2 are. Because depending on the way that you subtract, you could get a completely different answer in the end, and it's justified with your definitions. At least that's how it works with confidence intervals. So this right here is the statistic, that difference in population, or excuse me, sample proportions. We're going to subtract 0, and if you're kind of confused as why 0 is always going to be in that spot, well, it's the parameter. And if we remember from last time, the parameter always comes from your hypotheses. So the 0 value is going to be both in our null and our alternative hypothesis. So that's why we're always going to put it right there. And then you see you have your pooled sample proportion times 1 minus your pooled sample proportion over sample size for population 1 plus the same exact numerator here over sample size for population 2. Now, that is what I want to talk to you about. That looks slightly different from what's on your formula sheet listed as your standard error. Either one of these works, so you may want to just try and get used to using this one since it's going to be what is on your formula sheet for the AP exam. So if you want to put, that's the standard error, or you can use the formula right off the formula sheet that says the square root of pooled sample proportion times its complement times 1 over population 1 sample size plus 1 over population 2's sample size. These are algebraically equivalent. You probably want to practice using the one that you'll have in front of you. Now it asks, what does this measure? When we find the Z value, what does it measure? And it tells us how far the evidence is from the null in standard deviation units. It's the same thing that this told us in the last set of notes. It tells us how far the evidence is from the null, in SD units. That's what Z values tell us. How many standard deviations above or below, how far away we are from the null. All right, let's kind of practice some things here. Researchers in the UK conducted an experiment to determine whether giving the drug, I'm not going to try and pronounce that, in addition to usual standard care, would reduce the deaths among patients hospitalized with COVID-19. A total of 2,104 patients were randomly assigned, so this is an experiment, to receive the drug plus usual care. So there is our first treatment group. And 4,321 patients were randomly assigned to just get the usual care. It's like our control group. They aren't getting the drug. Overall, 482 patients in the drug group died within 28 days, compared with this many patients, 1,110, who died in the group that didn't take the drug. State the hypotheses, define the parameters, and state evidence for HA. So this is our state component. So again, we are going to work under the assumption every single time that population 1 is the same as population 2. You can write that like this if you want to. Or you can say, well, when I take population proportion 1 and subtract the second one, I get 0. These say the same thing. You're going to see both of them on the test at the end of the chapter, so be wary of that. That means that the alternative hypothesis is I'm trying to see, determine whether giving the drug reduces the deaths among patients. So I'm trying to see if the proportion of deaths that occur in my drug group is less than the proportion of deaths in my control group. That would go with this one. If you said that they were equivalent here, you would say that one is less than the other one here. If you're going to say that one minus the other is 0, then you would say that, okay, if this one is smaller, I'm trying to find evidence that the drug reduces the proportion of deaths. So I'm hoping that I find evidence that the proportion of deaths is smaller in population 1. When we take a smaller value minus a larger value, excuse me, that's not equals, you get something less than 0. You should end up with something negative there. So either give this set or give this set. Try not to mix and match, okay? Now, here's where we have to define the parameters. Where P1 is the proportion of deaths in the drug group. I'm going to keep it really simple. Drug treatment group for patients like these, or subjects like these. And you guys did a really great job on your test. Most of you are of remembering to put that verbiage on your test last time. Okay? And P2 is the proportion of deaths in the control group for patients like these. So we've stated the hypothesis, we've defined the parameters, we have a little bit of evidence for HA, and the evidence is that the proportion of deaths in the drug group, let's see, 482 out of 2,104 died, and that is going to be a decimal value that's smaller than the proportion who died in the control group. So 1,110 died in the control group. It's kind of a morbid problem here. And I'm just going to double check with some decimal values. So I have now verified that in the sample I've got a little bit of evidence that the proportion of deaths in the drug group is smaller. Alright, let's move on. I'm going to turn the page. Show that the conditions for inference are met. So we need to check, the only one that we're allowed to skip in an experiment is the 10% rule. So we need to make sure that patients or subjects are randomly assigned their treatments, or that treatments are randomly assigned to patients. And I did say that. Patients randomly assigned to treatments. Check. And we get to skip 10% because we're not checking for independence here, but we do need to check large counts. Now this is where things get really interesting. Okay, the first thing we need to figure out is the combined test statistic. And the formula for this is on your chart. It says the number of successes for each of the groups will be added together on the top. So that's 482 deaths and 1,110 deaths out of the entire sample sizes combined. 2,104 in the drug group added to 4,321 in the control group. So let's go ahead and take a second and figure out this value, because we're going to plug it into the large counts formulas. So it helps when you do your fraction template. And then I'm going to hit math decimal to have it switch it over to decimal for me. And we'll just say that that's 0.248. Alright, I really essentially have 4 things to check that are going to be greater than or equal to 10. Let's start with population 1. You're going to take the sample size times this value that we just found. Make sure that's greater than or equal to 10. It's about 522 if we round. And then we can fast track that. If 522 is the expected value, the expected number of successes, which it's kind of morbid to call deaths successes, but if that's the number of deaths out of 2,104, then that would leave 1,582 that didn't die, and that is greater than or equal to 10. All I've done right here is I've checked my population 1 successes, expected successes and failures. I'm going to go over here and check my second population. I get about 1,072. And then I'm just going to take that 4,321 and subtract out 1,072 to find that 3,249 would be my expected failures. Again, here, what I'm doing with the large counts condition is I'm checking for normality. And it is a tedious task, but everything works. All right. Now we get to calculate the test statistic and the p-value. All right. So in our test statistic formula, we are going to need the sample proportion of deaths in population 1, and we're going to need the sample proportion of deaths in population 2, p-hat 1 and p-hat 2. So the number of deaths that occurred, and I'm really just going to go back up here, and this is population 1, this is population 2, we just pulled them together. So 482 out of 2,104. We'll say that that's 0.229. And then we had 1,110 deaths out of 4,321. So we'll call that, oh, we already found this on page 1. P hat 2. Needed to pause and figure that out, because now when we do a statistic minus parameter, our statistic is really going to be P hat 1 minus P hat 2. Subtract 0. This is from the null and the alternative hypotheses. 0. That's the parameter. We're assuming that there's no difference at all in the population proportions. All over this bad boy right here. Let's plug into the one on your formula sheet. That's the standard error when you're comparing two population proportions. So P hat C is 0.248. The complement of that is 0.752. And then we're going to do 1 over the first group size, treatment group size, added to 1 over the second group's, the control group size. Ooh, thank goodness for our calculators here. All right, here we go. We've got a big fraction. And on the top, we need to do some subtracting. I'm not going to bother putting minus 0. On the bottom, we have a giant square root symbol. We've got 0.248 being multiplied by 0.752, open parentheses, alpha y equals enter, 1 over 2104, arrow over, plus alpha y equals enter, 1 over 4321. Close parentheses. Holy moly. This is how many standard deviations away from 0, the null, the difference in the statistic P hat 1 and P hat 2 would fall. Let's call that negative 2.439. So here's what we're now allowed to do. We've assessed for normality with the large counts conditions. We standardized everything. We're sitting right here at negative 2.4 standard deviations below the mean because it's negative. And we're going to shade the tail in. And we're going to use normal CDF to figure out the p-value. Lower, upper, mean, standard deviation. Let's figure that out. And I got 0.007. Okay, I want you to pause, and with me, I want you to, even though it doesn't ask you to, I want you to interpret this 0.007 because it gets really tricky when you're comparing the difference in two population proportions. So I just want to take a moment again, this is for Mrs. Lewis in case you're asked this in a multiple choice setting or for your response, to interpret the p-value. All right, we are finding the probability. This is what the p-value is. We are finding the probability that we'd get a difference as large or larger this right here, if you go ahead and subtract those statistical proportions, you get negative 0.028. Again, if you're like, wait, where did she get that from? I just want to know the probability that I would get the results, the difference of p hat 1 minus p hat 2, or even larger than that difference, by chance alone, if the null, or assuming that the null is true. And we're saying, assuming that there really is no difference in these population proportions, what's the probability that something like this that happened in the sample, the difference of those would happen, or something even larger than that difference? That's why I would go ahead and shade in that direction there. That was just a little extra. What conclusion would you make? All right. Because the p-value of 0.007 is less than, let's use alpha of 0.05, we reject HO. There is convincing evidence that P1 is less than the P2. The proportion of deaths in the drug group is smaller than the proportion of deaths in the control group. And that's as succinct as I could make that answer there. Okay, let me show you how to do something in your calculator. Is it okay to use your calculator for the do step? Obviously you can. Be sure that you understand, once again, you have to show the whole rigmarole of you plugging into this formula and the steps that you're using to find the p-value in the calculator. There's no way around it if you want full credit. Double check and be sure that what I show you in just a second, again, when you put successes and failures in the calculator, make sure they're integer values. That's why we rounded up here instead of putting, I don't remember what that was, 522.3. We went ahead and just rounded to the nearest integer because I've got all of this ready to go and put in my calculator. In your calculator, you're going to go to the tests menu, so stat tests, and you're going to do a 2-prop z-test. My 2's and z's look a lot alike, so 2-prop z-test. And let's see what it asks for. Stat tests 2-prop z-test, that's option 6. It wants to know successes from population 1, sample size population 1, successes population 2, sample size population 2, and we are, in this particular COVID problems, trying to find evidence that population 1's proportion is smaller than population 2. So I would enter in 522 out of 2,104 proportion of deaths. Population 2 was 1,110 deaths out of 4,321 assigned to the control group. And I'm going to arrow over to population 1 is less than population 2. I'm going to show you the draw feature really quickly. This is exactly what we had put in there. And then calculate. let me stare at this for just a second. Okay, sorry about that. I did that wrong. There's really no way for me to edit the video. So when you go to your test menu, I apologize. You are not going to be putting the expected number of successes and failure or successes in for the population. So you're not going to use the 522 and the 1072. You're going to actually use what happened in the sample. So 482 deaths in population 1 and 1,110 deaths in population 2. So I apologize. It's just like in the notes last time. And now I can actually show you the draw feature is cool. Because we were so many standard deviations to the left, there's our z-value that we found. So you can see the left tail is just kind of barely shaded. Oh, thank goodness, it makes me feel a little bit better here. Here's the p-value, okay? You would also get that on the calculate menu. So this will verify your math on your paper. I got scared there for a second. Okay, now this next little scenario is interesting. It says, are teenagers going deaf? In a study of 3,002 randomly selected teenagers in 1994, 15% showed some hearing loss. A similar study in a different year, 1,799 teenagers in 2006. Those are my two different populations, the 1994 group, the 2006 group. Well, it looks like there's been an increase in percentage of hearing loss in teens from 94 to 2006. I've got a little bit of evidence there. Now, this is interesting, you got to be careful. Between the two studies, Apple introduced the iPod. Yes, this is very dated, okay, but we are talking about 1994. And so we're just probably trying to see, hey, can we blame iPods for the increased hearing loss in teenagers? Well, of course, that seems kind of silly, but here's how you would justify it, like on a free response question. All we did is we made an observation. We measured hearing loss. So this is not an experiment. We didn't assign specific teenagers to listen to iPods while assigning some to not. We just observed the percentage of hearing loss. So because this is not an experiment, we can't blame iPods. That's not causation. Just put since we didn't assign treatments, like listening versus avoiding listening. To iPods, we can't conclude that iPods are the cause. I mean, lots of other things could be confounding there. So just to reiterate, for causation, we need both an experiment and statistically significant results. Both a well-designed experiment and statistically significant results. So if we really want to have some kind of, draw some kind of conclusion that one thing caused the results to happen, we'd have to perform a significance test and find out that there is evidence, but it would also have to come from a well-designed experiment. So turn the page, and even though we can't necessarily say we have causation, we can still answer this question. Do these data give convincing evidence that the proportion of all teens with hearing loss has increased from 1994 to 2006? So we can still answer that. That's not saying can we blame iPods. It's walking you through, hey, perform a hypothesis test. Let's use the 4-step process. Our null is going to be that there's no difference in the proportion of teens with hearing loss in 94 and 2006. And then our alternative is I'm going to just assign the 1994 to be the group 1, and we're trying to see if The proportion of teens with hearing loss then is less than the proportion of hearing loss in 2006. Proportion of teens with hearing loss in 1994, my population 2, or excuse me, my P2 is going to be the proportion of teens with hearing loss in 2006. We should probably go ahead and put the significance level here. It didn't ask us to do that on part A on page 1. That's why I skipped it. I didn't put it there. Okay. But since we're just left to have a whole bunch of blank space here and do the 4-step process, be sure to put your significance level there. And then we do have a little bit of evidence. Because it's explicitly said what percentage was that. So let's say 15% in 94. Well, that's less than the proportion of teens who had hearing loss in 2006. So there's our evidence for HA. Plan. We are going to perform a 2-sample Z-test for a difference in population proportions. That's as succinct as you can write that. I'm going to check for random. Teens are randomly selected, and it does say that. This isn't an experiment. Remember, that's why we couldn't find causation. So check in both populations that your sample size is less than 10% of the population. 3002 is less than 10% of all teens in 1994, and 1,799 is less than 10% of all teens in 2006. Large counts. Underlining just kind of helps the eyes of the AP grader know, boom, 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 check for all 3. So here's where we have to take just a second and figure out the pooled statistic. And that's going to be in just a second. Okay, sorry. We are going to have to actually figure out really quickly. In the paragraph, it just said that 15% of the 3,002 in the sample from 1994 had hearing loss. So we need to actually figure out the successes there. Well, 15% of 3,002 is 450. So we would say 450 out of 3,002 from the first population had hearing loss in 1994. And then the second one was that 19.5% of the 1,799 teenagers. So let's call that 351. Out of 1,799. Whew. All right. Alpha y equals. Go into my calculator. And I'm just double checking what I got before math. That's why I'm having to pause sometimes. Yes, okay, good. So 0.167. Now I have to do that and plug in to my large counts formulas. So let me show you. You can get away with this. You don't have to actually show any work here if you keep straight what you're doing. Alright, here's what I'm going to do. I'm going to take the number of people in the 1994 group multiplied by this value, and I get 501. I'm just going to put a comma. I'm going to list all 4 numbers that I'm checking to make sure they're greater than 10. But again, you have to think about what you're doing. You look at your last entry. Okay? The complement of 0.167 is 0.993. So now I have to check that that 3002 times 0.933 is also greater than 10. We're going to call that 2,801, comma. Now I'm going to check population 2. The 2006 group had 1,799 in it, multiplied by that 0.167. This is my expected number of successes, or expected number of teens with hearing loss, 300. And then I can do 1799 times the complement of our pooled statistic, which is 1,678. Those are all greater than or equal to 10, check. So you do not have to show the formulas for all of that. Okay, I think I made a mistake. Hang on, because I'm getting something a little bit different. Oh, I'm silly. I'm silly. The complement of this is actually 0.833, not 0.933. So that number and that number are going to be different. And the easy way to do it is just take 3002 and subtract off 501. Hello. Should have done it that way. 2501. Take 1799 and subtract off 300. I'm hoping most of you would have done that anyway. 1499. Okay, now I'm getting what I got the first time. Whew. Large counts, done. We've just assessed for normality. Do, this might be some of you your favorite part because it's kind of the same every single time. Statistic. Let's do population 1, or p-hat 1, which was 15%, minus p-hat 2, which was 19.5% of teens that had hearing loss that year. I'm not going to bother putting subtract 0. And we're going to practice using the formula for standard error on the back of your formula chart, which is this combined statistic times its complement that I messed up on earlier, 0.833, times 1 over 3002 plus 1 over 1799. And I am just going to double check for my sake. That's how I've been finding my mistakes. You can skip ahead on the video if you're waiting on me. This way I can just make sure I give you the right information. I did find a mistake. Okay, there it goes. holy moly, that's almost 4 standard deviations below the mean. So you're going to barely be able to even put that in your picture, which means we're going to get an insanely small p-value. -4, it's more than 4 standard deviations below the mean. Whoa. So expect your p-value to probably even be either in scientific notation, or your calculator might even just go ahead and round that to 0. So here we go, p-value. Normal CDF, lower, upper, mean, standard deviation, -1,000, -4.05. Right. And if we moved our decimal place 5 to the left, that'd be 0.00002. So essentially, our p-value is approximately 0. You could put =0 and it would be okay. Now we're ready to conclude. All right. Because the p-value of 0 is less than really any significance level we could have chosen, we reject the null. There is convincing evidence of population proportion 1 being smaller than population proportion 2. There is convincing evidence of that, which is that, and you can actually just use the verbiage from the question. Oops, it's at the top of the page. There is convincing evidence that the proportion of all teens with hearing loss has increased from 94 to 2006. We don't have to say in teens like these because it was not an experiment. And the last and most difficult part for some of you is going to be just interpreting this p-value, especially when there's a difference. We're testing a difference in population proportions. So we're assuming that the null is true. We always assume the null is true in a hypothesis test. So let's put if there is no difference in the proportion of teens with hearing loss from 1994 to 2006, there's about a 0 probability, it's kind of awkward to say, there is about a 0 probability of getting a difference as large or larger than the observed difference, which is that 0.15 minus 0.195 by chance alone. So if we assume that there truly is no difference in the proportion of teens with hearing loss from these one year to the other year, there's about a 0 probability that what happened in the sample, or even a bigger difference than that, happened just by chance alone. That's why we say that there is convincing evidence that hearing loss has increased from 94 to 2006. That one was kind of rough. I apologize for making all my mistakes. I hope that you made it through okay. I will be here next week every single morning if you need help on clarifying any of this. Thank you for your time.